Thanks. It's my turn to make the organizers for the invitation for this conference. Among so many friends. And okay.
Just to point. Is it on or off? You should switch it on the side, yes. I'll show you. The central button is the pointer. Not for the pointer. Okay, I show you. No. The central button is on. Ecco,
Here's the point.
Questi due arrow, devi puntare un po'. Provo a fare un cambio di pagina. Ecco, prova ora. Prova a fare un cambio di pagina.
Sì, funziona. Semplicemente la non è.
Anzi. No, è carichissimo.
Perché make use direct.
Sì, probabilmente sì, perché per qualche ragione adesso. Ma ho visto la seconda parte del talk di Luis. Prova a fare un po'. Che è successo? Non so perché. Guarda Diego, probabilmente ti converrà.
Uso questo, sì. Capito?
Sì. Mi spiace.
Devo fare qui.
Non serve ricambiare.
È andato.
Appena sei.
It's the right one. Yes. Okay. So the plan of the talk is about some qualitative properties of the linear equation with the point interaction in higher dimension. So not one dimension, but two dimension 2 and 3. So I will give the minimal summary of the subject of point interaction that will be not so minimal after the discussion of this day and some stimulating remarks. And then I will discuss well-posedness of the equation very briefly, and the two results that I would like to give regard two properties in two opposite regimes of the nonlinear Schrödinger equation: the low power regime, consider only the power nonlinearity, the low power regime where I will show the absence of filtering in 2 and 3 dimensions, and the 2D case, some results about the low up in the high power regime supercritical regime. And finally, I will discuss some perspectives. Okay. The topic is nonlinear Schrödinger equation with power nonlinearity, as I said, where the operator H is a point interaction. So a singular perturbation of the Laplacian operator used as a self-adjoint operator N2. The typical definition of this operator is by means of self-adjoint observation of the symmetric operator defined originally on the regular function out of the origin. And one of the main properties of this self-adjoint operator, the operator which is built after the extension, is that every domain element is characterized by a singular part. The sum of a regular part is a singular part. And moreover, when you consider an element in the domain of the operator, you can show that the above solution of the above equation, the abstract showing the equation of the above, solves a standard Schrödinger equation with the delta source. And okay, I keep this slide on the 1D case just for comparison with the quite different properties of the point interaction in higher dimension. The 1D case is very easy, and the point interaction amounts to a sort of a boundary condition of the origin that corresponds to a jump in the derivative proportional to the value of the function, which is continuous. And if quadratic form, the quadratic form of the operator is simply written, and this one, and you can see that the quadratic form allows to consider the operator as a simple form representation of the one-dimensional Laplacian. So, in some sense, you can consider the one-dimensional case as a sort of normal traditional Schrödinger operator with a potential which is a little singular at the origin. There is a lot of work on the one-dimensional case for a long time as regards purposingness, go-up, existence of standing waves under several conditions, stability, orbital stability of standing waves, and variation on the team. For example, recently a lot of work has been done on metric class, for example. But as I said, I'm essentially interested in the higher dimension case. Okay, in dimension higher than one, you need to consider the pointed direction as a whole, essentially. In no way you can consider a perturbation of the Laplacian, a regular perturbation of the Laplacian, particularly not the operator or perturbation of the Laplacian. And as I said, the traditional representation of the operator is a central joint extension with this domain given by function L2 that can be decomposed in the sum of a regular part and the singular part. The singular part is the singularity of the unit function of the Laplacian in the appropriate dimension. And there is a singular boundary condition at the singularity point. You consider just the single singularity, the unique singularity at the origin, and also consider, of course, several points, but I consider just the simple space. The alpha appearing in the boundary condition is the parameter describing the central joint extension, and the lambda is an accessory parameter not relevant because it's just the one that you use to characterize your coherent green function. Not relevant the following discussion. Okay, and so you see that the boundary condition relates the regular part with the coefficient Q of the singular part. The action of the operator is this one, the operator X on its domain elements as the Laplacian X on the regular part of that element. And you can also consider this alternative presentation, which the distribution, the delta distribution of the origin explicitly appear, and you have to take into account that the Q depends on the psi of the plane properties. H alpha, the point direction is a local operator. It's just this property. Direction is zero. So if zero does not belong to the support of psi, the action of the point direction coincides with the action of the Laplacian, and the direction is not delta because of this fact. And so is a proper operation called delta interaction, but it should not be confused with the Laplacian plus a delta at variance with the one-dimensional case. Spectrum, the spectrum is as a continuous part, which is 0 plus infinity, and there is a discrete part of the spectrum depending on the dimension. In dimension 2, you always have a negative eigenvalue. Whatever be the parameters of separate extension, and in dimension 3, you have a negative part of the spectrum with a single negative value, simple negative value, only if alpha is negative. You can also construct the associated quadratic form, and which is the domains, the domain of which is the finite negative domain. Again, the quadratic form is characterized by the fact that the element of the domain is decomposed in a regular part and a singular part. The singular part is again the green function, and the regular part is H1 this time. Okay, but after this try list of properties, I would like to discuss, following some questions of these days, a way to introduce the point interaction, and we focus on the DP case, which in some sense, one of my favorites, by the way. There are several ways, but this, my opinion, is especially instructive, and is the introduction by means of perturbation of the Laplacian by means of a rank 1 perturbation, which is the projection over some form factor of epsilon. And what I want to discuss, what I want to show is that carefully choosing the coefficient epsilon dependent in front of the rank 1 perturbation, you can get something which is meaningful and coinciding with the point interaction. In particular, I want to show that if the scaling of the rank 1 perturbation, the function form factor described with the rank 1 perturbation is the one of the delta, you have to choose carefully the coefficient in front of the perturbation to get something meaningful and not something trivial. Now, you can write explicitly the involvement of this simple perturbation of the Laplacian, and you get this expression. So the operator, the resolvent is just the resolvent of the Laplacian, the free Laplacian, plus a term, which is again a rank 1 perturbation, more regular, of course, the resolvent. And this time the function where you are projecting onto is this one. So the free Laplace equivalent of the function applied to the epsilon. And you easily see that, of course, when epsilon is going to 0, this term is converging to this function, which is again a way of representing the unit function. And the coefficient in front of the perturbation can be rescaled this way, and it has this behavior when epsilon is going to 0. We have the term which is diverging and the term which is constant, and a remainder which is infinitesimal. Now the L, the coefficient of the diverging term, is just the energy of the function. So, okay. So what you have to control the end is the box term, is the diverging term, which this one, and immediate analysis shows you that, of course, the coefficient A in front of the tangent term behaves this way, so 1 over A gives the other way, and you can absorb the divergence just requiring that the coefficient is chosen in this suitable way. So the minus sign on the L just eats the divergent term, and what this simple analysis shows, simple but not trivial analysis shows, is that, for example, consider the operator level. If you redefine your approximated operator H epsilon this way, so choosing the coefficient in front of the diverging term, the delta term, say, in this way, you get something which is well defined in the limit, because the resolvent limit that exists is this one, and it can be shown that it's the resolvent of the self-adjoint operator, and more precisely, it's the resolvent exactly of the quantity tension. If you choose a different coefficient in front of the singular term, you get the triviality of the operator in the limit. So this is a kind of renormalization.
Is there any way to get the same limit operator by Noja first order regularization?
First order means just neglecting alpha. Yes, you get one of the self-adjoint extension, only one, the one with alpha equal to 0. And the remark is that actually the needed term, equation, which is gives me the opportunity to make a further remark. The needed term is just the one alpha equal to 0. The other one is ability. The disability term gives you some alpha. You want some alpha equal to 0. You get to add this term in the say correcting A, correcting efficient of singular relation. If not, if you cancel this epsilon term, you don't get you just have the trivial. So this term is the needed one, and in some sense is the resonant term in the construction. So this is the final way to build an approximated operator, and if you use this, you repeat the construction. Of course, you get the result. So this converges in the normal result sense, by the way, the point direction. And so this is another example of normalization cited these days in different examples by Willis for the velocity, and yesterday by okay. By the way, this is some sort of toy model of representation point. Okay. Yeah. By the way, this is a local approximation. A local approximation can be considered as well known, and it's commonly used in most of the description of the subject. But in some sense, it's more complicated. By local approximation, I mean an approximation by means of scaled potential. And in particular, for n equal to, you can show the work done by Valerio and Ultron in the 80s. You can show that this scaling, you have to modify the delta scaling this way to get something in the limit, and the something is just the point direction information too. And for n equal to 3, you have to scale the delta scaling. You have to modify the delta scaling this way to the same code. So in any case, the moral is that you have to tame the data in some way. Okay, and the further information which is relevant is that dimension 3, the procedure works just only if the original local Schrödinger operator is a zero energy response, or in the language, P is an exceptional potential. If not, you will get again triviality limit. So the free data function. And by the way, one ask itself or herself, what about the non-local approximation about this item? And the result is that you always have a response. And this is probably the reason why the procedure always works, and not under condition, under perfect condition on the there are many details, more details that can be even in a recent paper by Alessandro and other co-workers showing the lot of details and other scalings that you can discuss. Okay. Now we come to the main subject of after this introduction. I come to the main subject of the talk. And we come back to the Schrödinger equation. I will briefly discuss some information obtained these last years about the boldness. You can guess that there are difficulties due to the singularity of the green function because of the power. And this reflects in the fact that, for example, in dimension 3, if you want stronger existence of the solution, you have to consider just low powers. Because not you go out of the operator domain and the existence of the solutions. The fact that the local singularity of the green function to be is just a log make much easier the situation, and actually the existence holds true for the same power where existence holds true for the normal standard story. And the other properties go in the usual way. For example, you have the last alternative. And concerning instead the energy domain, the less regular solutions in the form domain, the operator, the situation is a little bit better for the three-dimensional case because there is nothing written, but it's expected that the existence is also for where in two dimensions there is a result due to la linear and Keda is result leading what was saying that the equal 3 is not written, but expected that the existence also for exponent p lower. Again, due to the limitation imposed by the green function belonging to the right space. Okay, there are also other results may be discussed more by Mario Raffaelli, but we'll wait for knowing them. And the situation is also clear and studied for the RP model, again by results by geography results. Okay. Now, comments I already gave these comments. So, okay, there is a concentration of the energy whenever the local holds true. And so you can discuss for the global when suitable, for example, equal to the global potence also for every power p lower than 3, so just as in the standard case, the focusing case, and of course very big in the focusing case. And for equal 3, global potence in some sense not an issue because the power is low. Is low. So whether the global potence whenever you have the because we just have the operator domain be lower than 3/2 and in an energy domain be lower than 2, which is too low to give the interest of the equation. So in some sense, in this sense, the three-dimensional situation is somewhat dissatisfied. At least in this presentation. Okay. now I come to the two asymptotic regime I discussed, I announced before. The first one is the one of long-range nonlinearities. Long-range nonlinearities means low power. And what we are interested in is the scattering. So we want to compare the asymptotic behavior of the free dynamics and the interactive dynamics. The linear level, you have the Schrödinger operator, standard Schrödinger operator, this one, and the standard hypothesis on the potential we expect an asymptotic dynamics of this kind. The composition in bound states, evolution of the bound states, the free evolution is the scattering part of the continuous part of the spectrum plus the remainder. And you would like to know how much this picture transfers to the linear equation. This is a very good topic in generality, and there are results, of course. The final goal would be to say something about the found each conjecture. So to show that asymptotically the evolution of the solution of the linear equation is the bound part at the solitons the linear level is scattered in waves and the small remainder in some topology. Sometimes the smaller remainder is called radiation, sometimes the scattered in waves is called radiation. However, this is the picture. But as you know, this not proved, not shown, if not in some very special cases. And the special cases are essentially integral systems, where however the techniques are completely different from the usual techniques of these, but this is not the problem. The problem is that the hypotheses are wrong, especially on the decay of the initial data. And there are other few cases, for example, typically very few cases in essentially geometric wave equation. Just no those examples. Okay. Now, now we jump to our linear Schrödinger equation, and we consider the linear Schrödinger equation for low power, and heuristically, a nonlinear term such as this one can be considered as a sort of potential multiplying the psi. And considering the dispersion of the Schrödinger equation, this sort of effective potential is slowly decaying if you consider low powers. And this is the reason why such nonlinearities are called sometimes long-range nonlinearities. It's well known that in the standard linear Schrödinger equation, the scattering does not occur, in the sense that if the decomposition given this way in a tube for equal to part infinity, psi plus is the classical result due to Gastry and Strauss dating back to the 70s. And similarly for arc pregnant. In a recent paper by Dr. Nakanishi, it has been shown this factor has been generalized to Schrödinger operator with several hypotheses depending on the dimension. In particular, in 1D, their hypothesis include that the observation of the Schrödinger operator can be measured. Bounded variation, and this hypothesis allows the presence of delta functions, not only one. So the question arises if this result, absence of scattering in the relative equation of the point interaction, also for dimension 2. And this is actually the situation, and we have a result of this kind obtained with value measure quality and doing the Pico. Suppose that we have a solution of the Cauchy problem of the Schrödinger equation with a point interaction, and just suppose that it is global in the future. Sorry?
Which space average?
No condition, if not globality to the future, for example, it's not important. You just need the details. So it's a sort of black box situation because it was just the asymptotics. And suppose that the representation of the boxed form or boxed equation holds true again in 2. So the psi, the future is asymptotically decomposed as a free wave, a free evolution plus a bounded term in some LP space and the radiation. Now, if the power P in 2 dimensions is lower than 2, same as in the classical case, and the power P in D equal 3, dimension 3 is lower than 4 or 3, psi plus is T. Psi plus is T. The bounded term can be present or not. If you consider the forking Schrödinger equation, the forking Schrödinger equation typically you will have orbital waves, also other solutions such as Brevers or similar. And of course, if they are out of the bound component in the linear case. And I should notice that the Murphy-Nakanishi result gives a wider range of powers in D equal 3 as usual. So the same for D equal 2, and for D equal 3, they catch the range P between 1 and pi over 3. Their hypothesis on the potential in that case, if I remember, is E belonging to L E L over 2. So 3 over 2. And probably we lost something due to the singularity of the point interaction, and as we see, due to the lack of outward inequality, essentially. Okay. The tools by means one can show these results are different from the one used by Murphy and Nakanishi because they consider the potential as a perturbation of the Laplacian because of the hypothesis, integrating the hypothesis of the potential something else. It is the item 3 or equal to 3, and this is if I will remember one class, it will be equal to, and D is a measure bounded variation of equal. It might be some other condition. But we have to use more directly the properties of the point interactions, and in particular, we use a more detailed description of the scattering, the linear scattering properties of the point interaction. In particular, we know that for the point interaction exist generalized functions, and by means of the generalized function, we build a Fourier distorted transform that satisfy the usual properties. In particular, you can build the wave operators. Operators exist, and wave operators in cellular regime have been studied by Vladimir, Alessandro, Raffaele, others. And you have the usual property of the evolution by means of this Fourier distorted Fourier transform. The M and D operator are the Dollard operator used traditionally in this kind of. And okay, this is the explicit expression of the distorted Fourier transform. And the important point is that by means of the property, the important properties studied by Cornet, Grandi, Yashima in dimension 2, Grandi, Scandoni, Yashima, and others, and Antonio and others in dimension 3, one can show boundedness of the wave operators in some power regime that were any power regime equal to, and sorry, power x with and q belonging to 1 and 3 for equal 3. This limitation is the one that limits also the existence of the Hausdorff-Young inequality for the distorted Fourier transform, and this is also the final reason why we have a result weaker than the one of Murphy-Nakanishi as regards our powers and the linearity of the Laplacian equation. And the proof is done by contradiction and is similar to the original scheme of the proof of Blessing. And suppose that the composition holds, which we given before, soon, you can replace the ablation with the point interaction. It's immediate, and then you consider this B, this quantity B, which is bounded, is being shown to be bounded. Then take this quantity B, where psi is psi solution, and W is the evolution of some suitable test function to be chosen according to the limits. First integrate and then use the equation in linearity. then scale, and you get this expression. Where psi tilde and W tilde is the application of the relation and multiplication directly given before on the W. Now, the power, the previous power is not integrable at infinity under our power hypothesis. And so, to get the proof to show the results, it's sufficient to show that this function exists such that this quantity is definitely inside. For example, is possible. And there's some manipulation. You show that you need just this asymptotic behaviors. F is the nonlinearity as I said before. The first one, the first condition is easier, and the second condition is less easy because after getting explicit in terms of the values rate of appealing, you fall down on a certain integral operator, and you have to make use of some properties of some acute multipliers steering in the expression, and so you make use of the quantity to show some boundaries, but I will not give details. I stress again that the restricted exponents in the Hausdorff-Yang inequality are the consequence of the lack of the boundaries of rate operators and lack of existence in the Q power, the Q space, and the space of the Hausdorff-Yang. Okay, I skip the details because I would like to say something about the block. Okay. Well, okay, for in dimension 2, one expects block. The typical strategy we use these results obtained with the domain of info here. And typical strategy is to consider the variance. And so restrict a bit the energy space to the function respecting this condition. And you consider the variance of the function psi. And after some calculation, you show that this function satisfies some typical real identities. The one we need is the one related to the derivative function. And so you discover that this second derivative can be written as the sum of the multiple of the energy, plus or minus depending on the focusing of the defocusing character of the equation, and this further term, or in terms of the product form this way. You call this quantity Q. This is a function of Q, and the Q function of Q is written this way, or the other way is the energy. But the relevant fact is the presence of this anomalous step, which is the term. This term contains the charge of the side, the singular part of the element domain elements. Sorry. And this term is without sign. It's positive, strictly positive, whatever be whatever the sign of the for example, of the alpha characterizing the spectrum of the point interaction. So, in particular, this sign positive, not conserved, and for example, the simple result of the graph with the initial data with negative energy phase, because we have the fixed curve which is always stop. The only interpretation I can give about the calculation is that point interaction dimension 2 always has a negative, whatever be the outcome. And it is a negative way. Negative way, whatever be the outcome. So you cannot expect something, some aid from the spectrum.
This is because the dimension is good.
Yeah. Just the dimension. Dimension 3, the issue, the problem is not meaningful because existence is only the global existence is for all powers. And so global existence always is true in the standard, at least in the standard mathematics. So energy domain. So the blow up is meaningful just in dimension. But I have not an explanation of the positivity, the presence of this anomalous term, which is physically meaningful, apart from the one very formula that I just gave. Okay, now considering the minus sign and the equation for the equation, you want to show that the blow up force and how many minutes or seconds you
Yes, and there is 11 minutes.
Okay. 11 minus. Okay. Yeah, and just yeah. Okay, so to show the occurrence of blow-up, we rely on some properties of standing waves of this model, and so a standing wave well known is the solution of this kind, something has been said being discussed by Raffaele on Tuesday and will be discussed by tomorrow morning. I guess the speakers of tomorrow morning, so I eager to know the news by then. And okay, standing wave is a stationary point of the action, functional, as usual. You can define the ground state, the state of ground state of the action as the elements of the domain satisfying these properties and this kind of linearity properties. And recently has been shown by Vladimir Nikeda and independently different strategy by Giordano Monica and Tattarelli that ground state exists, and constrained ground state exists for traction, the case of tracking linearity, and in particular when omega, when the parameter of the standing waves is higher than the eigenvalue, the unit value of the H alpha, you get that this term is actually, the omega is actually attained when n omega the constraint meant for this the alpha, is given by the alpha. Okay, and okay. Now, what you have to do? The idea is the usual one. You have to show that the second derivative of the variance is concave and describing a positive quantity at some time at the start, the solution does not exist anymore. And to show this, you have to overcome the difficulty given before, and you have to build a set of the phase space of the problem which is invariant, and where this property also. So where you can show the negativity of the second derivative of the variance. And this invariant set, the easiest of this invariant set, this one, to consider phi, where the action is lower than the action of the ground state, energy is positive, and Q is negative. And with this hypothesis, you can show that it is an invariant set. And on this invariant set, you get the condition, the period condition, and the existence time of the solution corresponding to psi zero in this chosen in this invariant set is lower than classificated. The existence is only local time. The crucial point is, of course, is to overcome the issue given before, and in particular found the period functional or function to the set. And this is a strategy already used by Noja and others, in others not by also by Gaia and others in several models, including the reaction equation with the Coulomb potential or generalized potential, if I remember. There is a potential in one dimension, and also a model on sarcasm. So one dimensional case is one dimensional delta potential, or more general dimension, but with more regular. And okay, and moreover, you can also show that the standing waves are strongly unstable, and this means that consider the standing wave before a standing solution before, and you can show that there is a sequence of initial data converging to that standing wave, the profile of the standing wave in energy, such that evolution on that sequence of initial data is going up in the future, or in the past and future same. And okay, so for the variance set before, and for this in this hypothesis, any standing waves is strongly unstable, so it's approximated by initial data in the future. Okay, there are also something a little bit more general conditions, but I'll skip this certain examples. I only noticed that concerning the positive energy conditions means, for example, to consider conditions on the size of omega. So, because when omega is bigger and bigger, you you come more near and near to the critical flash. And you know that for supercritical powers, the energy of the standard Schrodinger equation is positive. So getting Eiger and Eiger the standing waves means in some sense you can scale the operator. They can show this frequently going toward the free Laplace and the standard Schrodinger equation where this condition is not. I have not particularly estimated that. So I think I can stop here. There are some maybe some conclusion, okay, but in perspectives, and just perspectives because this is the title of our workshop. And okay, there is what causes in more general situations, but I think something will be said soon. I am curious of the existence and stability of excited states for the 2D in the business of theory. There is the difficult topic of the asymptotic stability. And particularly in 2D, there is an ongoing work with how you catch a way of thinking in the case of small standing groups, which is the easiest case. Or solution for standing waves that are not small. The situation is much more difficult. And also in the one-dimensional case, far from being clarified because of the various problems with the spectral theory of the and only numerical results are known in the case, numerical indication of results. And there is, in my opinion, also an interesting chapter not yet developed about the one about which discussing something Raffaele Tuesday. And so the relation between point interactions and the singular solutions, the singular ground state, they are so-called in nonlinear operators. It's a completely independent story. Began with Sergin in the 50s and then developed the semi-linear equation. Like this is Veron so and then it is very interesting in the relation which on one part you have a definition of point interaction essentially or the nonlinear equation associated with point interaction as perturbation of point. On the other side, you have a not a nonlinear operator from the beginning. Because the singularity is embodied the operator. And so you get some, they are results related essentially to the extension of classical results about a function to near characterization of singularity of any of elliptic operators, also in but I think I can. Many thanks.
Well, thank you, Diego, for the nice talk. Any questions?
So, regarding this spectral theoretical criticality of the dimension two you spoke about, the fact that whatever alpha is, you always create an eigenvalue. I would be curious to know about a possible competition of interaction with an analog bond potential. And do you expect in that case the possibility to create a kind of threshold value for alpha?
I think there are questions and there are people in the audience much more interested than me about this relation between dimension two between the arm form potential, the Schrödinger equation between the arm form potential and the sum junction, the perturbation by this point. Surely there is a competition, and so different I think sort of bifurcation.
I would say that the starting point should be the big identity. You should see that after small alpha, you don't have this.
Yes, I think in the sense the result represents of our potential, which is somewhat similar to the one described by same behavior theory into it. But I think there are some working problems of this the spectral linear way. Not like
Other questions?
Actually, this question is somehow influenced also by the total things, because what we have here, one point, fixed point. On the other hand, when we have curve, this is also kind of structure that you combine with, in his case, Navier-Stokes or some kind of parabolic type equation. In this case, we connect Schrödinger. Of course, between Schrödinger and Navier-Stokes, there is nice connection. But my question is, if your singularity start to move, wave operators, what will happen if we have some?
This is a very, very difficult problem. There are some results about radial singularities, and in the early days, I made an attempt to study moving singularities in 3D ways. So the idea was to describe the linear operator corresponds to this moving singularities in the Schrödinger case, when you consider Schrödinger dynamics, something exists and is due to Andrea Bottini. In the wave case, which is most interesting to me, essentially it's much more to the loss of regularity caused by the wave evolution. But the interesting point is, in my opinion, this one. You have this structure, psi is equal to psi reg plus q G. The Q is depending on time and the ground, so the psi, and you impose some further condition on the evolution, for example, some conservation, global conservation law, and you want to understand which is the evolution of the Q, which is in some sense the position of the singularity, the particle. And this is very difficult, and in the wave equation is difficult for the reason of the loss of singularity of the regularity to the wave evolution. In the Schrödinger case, nobody attempted to do this. Formulas are more difficult, but with more regularity. Because the evolution is difficult to discuss the evolution of this quantity in the Schrodinger equation. Because you fall in some integral difficult operations. But my main interest is to understand the behavior of this quantity in this case of moment. There is another less, not less rigorous, say more formal kind of analysis for several equations due to John Neville. Neville was an applied mathematician in California who studied a similar problem in the two-dimensional case with an eye to the evolution of vortices. And so more similar to the interest of Lewis. By making use of mentioned asymptotic expansion around the path of the law. And but not only and he did this for the integration, the wave equation, and some geometrical wave equation. And these are partly formal results, but very interesting. Nobody came back to those results. I think they contain some interesting, at least around 90s. And they contain, in my opinion, they contain interesting suggestion about this property. The results are, from the point of view of applied mathematician, and he makes strong use of the technique of mentioned asymptotic expansion, but I think it would be interesting to develop say in the main moving signal. So you want to get a closed or almost closed equation for the coefficient of the singularity, which is the behavior of the particle. Can be the vortex, a line of say in the case of wave equation, geometrical wave equation, you have some kind of fracture.
Other questions? Okay. If not, we can then